topic's talk is going to be qcow2, why not? I'm Max. Kevin's still sitting there, but he'll come up on stage later. And, well, the question is in the title. Should you use qcow2? Why or why not? The question comes up every time you're creating a new virtual machine. You basically have the two main choices for QEMU. You have the system default chosen by libvirt or virt manager, which is qcow2, or you have the raw image. And the traditional answer is just, well, do you need performance or do you need features? If you need performance, you choose raw. If you need features, you choose qcow2. But, well, what do you do if you need both, which happens most of the time? So you can't think really hard about whether you really, really need the features qcow2 provides. And, well, maybe you can get away with them, so maybe you can go for raw in that case. But choosing a car analogy, because we all know car analogies are the best way of explaining everything, it's like throwing out the seats in order to gain more acceleration. So you can go around in your car with more speed, but you're standing up, which sounds like a horrible idea. So the question is whether it's really worth it. And the same applies to disk images. We want you to keep the seats in. That's our goal. You should just be able to use qcow2. If there is even a slight chance that you need any of the features qcow2 provides over raw, then you should just go for qcow2. And don't worry about the performance impact too much, because it should be minimal, if possible. And whether that's possible, that will be the goal, the topic of our talk. So first part, what are those features qcow2 provides? Well, we have backing files, we have internal snapshots, we have zero clusters and partial allocations on all file systems. So with raw images, you can have partial allocations on most modern file systems too, but with qcow2, you get it everywhere. And also you get compression, which may or may not be useful to you personally, but it's a feature qcow2 provides and raw doesn't, so it's listed here. Let's talk more about how qcow2 is organized. Every qcow2 file is split into clusters, which by default have a size of 64 kilobytes, and each cluster can store either data or metadata. At the bottom, you see the empty clusters which don't contain any text. Those are data clusters, except for the one to the far right, which is an empty cluster, and the other clusters, they contain metadata. So for instance, the cluster to the left, most to the left, that one is just the image header. One kind of metadata we have are L2 tables, which map guest offsets to host offsets. So every time you are reading or writing to a qcow2 file, data that is, you're using a guest offset. That is the offset a guest would use on his disk, or on its disk. And the L2 tables are used to map that offset to an offset in the host file. And then QEMU knows where to get that data from if you're reading, or where to write it to if you're writing. The refcount blocks are used to store allocation information. That is, most clusters are used exactly once, so their ref count will be 1. But some clusters can be used more than once. So for instance, you see the two data clusters to the right. They, on the guest, they are actually shared. They point to the same cluster in the host file, so they will contain the same data when reading them. But they will contain different data when writing to them, because in that event, a copy and write operation will be issued. That is, you're writing to one of the clusters, that cluster content will be copied to a free cluster, and then the data will be written there, whereas the other cluster will remain untouched. And this information about whether a cluster is shared or not is replicated in the L2 tables, so that when we are accessing a qcow2 file for a data access, we generally only need to look at the L2 tables, because the L2 table will tell us whether the cluster is referenced exactly once, in which event we can just write data to the offset in the host file, or whether it is shared, in which case we have to do a copy and write operation. And when doing a copy and write operation, we have to look for a new cluster where we can write the data to, and that's where we need the ref count blocks, because then we need an empty cluster which has a ref count of 0, and that's what the ref count block is then used for finding such a cluster. But in the general case, we get away with just using the L2 tables. So for most I/O, the L2 tables are the most important metadata structure, which will become more important later on. So let's come to a more interesting part, performance testing. First, we'll take a look at pre-allocated images. That is, images that have all the data, or at least the metadata already allocated, and pretty much the data too. That means that every I/O we will execute on that file will not need to allocate a new cluster in the qcow2 file, but we can just execute the I/O, only looking at the L2 tables and just do the I/O. What this benchmark will or these benchmarks will tell us is whether there is any fundamental problem in qcow2, and that there is really a systematic problem in qcow2 that just makes it slower than raw. So we look at that, and we hope that there is no such problem. The thing about pre-allocated images is that you cannot really use all of the features qcow2 provides you with them. So for instance, you cannot have backing files, which is sad, but let's just take a look. If they're as fast as raw, that's a good first result. And Kevin will take a look at non-pre-allocated images with backing files later on. So what is tested? I used a Linux guest with FIO as the benchmark tool. I used 6 GB images on an SSD and an HDD, and I had 4 different access patterns per test case. So we have random 4K blocks, random 1M blocks, sequential 4K blocks, and sequential 1M blocks, and then we'll see both read and write accesses. As I said, the qcow2 images were created with the option pre-allocation equals metadata because that makes them faster. So it's a better comparison against raw because, well, we can see whether qcow2 is fundamentally slower. So let's take a look. This diagram shows the comparison of raw performance, which is on the left always. It's the blue bars against qcow2, which are the red bars, and each stack is normalized against the number of I/O ops of the raw image. So higher generally is better. The error bars signify the standard deviation, and I consider everything that's within standard deviation to not be significant. So as you can see, standard deviation is pretty high, but I cannot really reasonably make the test any longer than 120 seconds because running these tests already took like 6 hours. So yeah, well. And the standard deviation doesn't really get lower. So, well, we have to live with that. But what we can see is that there is no significant difference outside of standard deviation between raw and Q for write accesses on an SSD, which is nice. We can see the same for reads. No significant difference. Same for HDD writes. And the same for HDD reads. Well, that's great, right? So if you use a pre-allocated qcow2 image, then it's just as fast as a raw image, right? But, well, we use 6 GB images. That seems awfully small. Well, is there some reason for that? Maybe we should just increase the image size to get a more realistic approach, right? Okay, let's use a 16 GB image on an SSD. Oh, wait, that doesn't seem right. Suddenly, the performance for 4K random writes dropped to like 60 to 70%. And as you can see, the standard deviation for 1 MB random accesses is pretty high, so that seems to indicate a problem too. It gets even worse for reads. Standard deviation for 1M random accesses is again pretty high, but the performance for 4K random reads is just abysmal. It's just above 20%. That's horrible. Can't work with that. So, well, what about an HDD 32 GB image? Basically the same result, only this time 1M random accesses are very, very bad too. And it's basically the same for reads. We actually have a performance penalty, in this case for 4K sequential accesses too, so okay. That doesn't seem too nice. So what happened? Cache thrashing happened. qcow2 is caching the L2 tables, so you don't have to look at the L2 tables on disk every time you're doing an I/O access. And the default cache size is 1 MB, which covers about 8 GB of an image. So once the images got bigger than 8 GB and we had random accesses all over the place, the cache was no longer effective. And qcow2 had to look at, and QEMU, the qcow2 driver and QEMU had to look at the I/O table, at the L2 tables on disk all the time. So that's why the performance just went down. How can you fix it? First idea is don't panic. Maybe you don't need to fix it at all. Because these were tests where you had random accesses over an area of 16 or 32 GB of an image, which is probably not what normal applications do. So as long as you don't have an application which actually does these accesses, which does random accesses all over the place over an area which is larger than 8 gigabytes, then everything's fine. The actual image size doesn't matter. As long as random accesses are contained within a small area of the image, everything's fine. You don't need to fix anything. But if you do need to fix something, you can. There is the L2 cache size runtime option, which allows you to adjust the size of the L2 cache. And a term to calculate the cache size you need is given below. You just divide the size of the area you want the L2 cache to cover by an eighth of the cluster size, which by default is 64 kilobytes, so an eighth would be 8 kilobytes, and that's the result. So for instance, for our 32 gigabyte image on the hard drive, we would then use 4 megabytes as the L2 cache size. So let's try again. For our 16 gigabyte image, we would need at least a 2 megabyte L2 cache. And now everything's fine again. Great. For writes and for reads. Trying again with a 32 gigabyte hard disk image with a 4 megabyte L2 cache. Looks good again, both for writing and for reading. So that's nice. So what this tells us is that there is no significant difference between raw and qcow2 for pre-allocated images, as long as the L2 cache is large enough, which you or your management tools have to make sure it is. So that means without copy on write accesses, everything's good. But, well, the format is named qcow2 for a reason, right? You probably want backing files most of the time. So what happens then? And that's what Kevin will talk about in part 3.
Yeah, so as Max has told us, if you don't actually use the features that qcow2 brings to it, everything is fine, but at least if you take the right options. But usually you use qcow2 for a reason, and that reason usually contains backing files. So you don't use pre-allocation in the usual case, but you start with a sparse image that is an overlay of a backing file, and you get cluster allocations, which change the picture a bit. They don't change the picture a lot for reads, but they do for writes. And that's the old problem that we have been talking about many times already. So when do we actually allocate a new cluster? A new cluster is allocated when you write to the image, to an area of the image that is not allocated yet. If you have a backing file at this point, if the guest was reading from this area, it would actually see the data that is stored in the backing file. If you don't have a backing file, it's just all zeros. And then there's the other case where you get copy and write. The cluster already exists, but it was referenced more than once. That's one of the cases that Max showed. Actually, there are two cases where this happens. One of them is internal snapshots. So you have multiple snapshots pointing to the same cluster in the image file on the host. And obviously, you don't want the snapshot to change when your current running guest is updating some data on the hard disk. The other case where you get copy and write is compressed images, because in that case you have multiple guest clusters, as the guest sees them, stored in the same cluster in the image file. So the guest cluster only takes up part of the cluster in the image file, and you can't override it. You need to allocate a new cluster for that. So what happens when you do an allocation is you get a whole cluster. The cluster is usually 64 kilobytes. It's configurable, but that's the default. And the guest may write with less than 64K. It might just write to some part of the cluster. But when you allocate a cluster, all of it needs to be valid. You can either map a whole cluster to a cluster in image file, or you say it's not there. So if it's there, and it has to be there when the guest writes to it, you write the data that the guest provided into it, but if it doesn't fill up all of the data in the cluster, you need to fill up the rest of the cluster by just copying in there what was already visible to the guest. That is either data from the backing file, zeros, the old data from the internal snapshot, the cases that I just mentioned. And that's a copy and write operation, and that's what makes things slow, because it involves quite a bit of work. So I have 3 different problems that I want to talk about. One results in more I/O requests, the second one in more bytes transferred, and the third one causes more disk flushes. And all of this makes copy and write slow. So the first problem is, how do you do this copy and write operation? The obvious naive implementation is you just write what the guest gave you, then you read what's in the backing file for the part before it. You write the part before it to the new image. You read from the backing file, and you write it again. So you have 5 I/O operations for the naive implementation, and needless to say that this is exactly what QEMU does. This costs about 30% performance compared to a rewrite. So a write to a newly allocated cluster is 30% slower than if you write to it again. It's easy enough to just have a single write instead of 3 different writes, so you have only 1 request, and that actually improves the performance if you don't have to read from somewhere. So if you don't have a backing file, you just prepend some zeros and you append some zeros to the buffer that is passed by the guest, and you have 1 single write request instead of 3, and it almost restores the performance. It doesn't make a big difference if you write just what the guest requested, or the big chunk that includes some zeros. But as soon as you have a backing file, you need the reads, and even 1 read is expensive enough that it doesn't actually help much. The second problem that we have is that we're actually doing a lot of copy and write that's unnecessary, because we have sequential writes, and as you can see here, we start with a write request. The new data is what the guest actually wants to write, and the red ones are the areas that we copy from the backing file to fill up the cluster. The one at the beginning we actually need to do, just to be correct. The data needs to be filled. But the second one is immediately overwritten by the next write request, because we're doing a sequential write. And again, it's doing some copy and write at the end, which is unnecessary again, because the next write request will override it immediately. So we're doing a lot of unnecessary work. We don't have to copy all of the data at the end of these requests. So what we want to do is, if this copy and write area is overwritten, we just want to avoid the copy in the first place. And I tried a few things to do that. It got complicated and more complicated, like tracking all the requests and checking what overlaps and stuff like that. And then at some point I remembered that we had a similar problem with metadata performance like 5 years ago. And what simplified the solution much was when you stopped doing all these complicated things, but actually just introduced a cache. So I thought, let's do the same here. Instead of just having a metadata cache, we can have a data cache as well. And the idea is when you would have to read from the backing file in order to do the copy and write, you instead allocate a cluster in the cache. You don't actually do any disk I/O yet. Put in the data the guest is going to write, and don't read in yet what's in the backing file, but just mark these areas in the cache as invalid. And you only read them if you actually need them. That is, when the guest does a flash operation, or when it reads, then you have obviously to read in and complete the copy and write. But if the guest writes to the same area in the cache, that makes the cache valid. You don't have to actually read anything in, and you get a fully valid cache cluster in memory and can write it out at once, and you've saved all of the reads and get down to a single write. So that actually seems to help a lot for me. As you can see, for rewrite, it doesn't make a big difference. Actually, it shouldn't make any difference. That's not really significant what we can see there. But for the small writes, we can see that it makes a huge difference. So in QEMU.get master, that's this small blue thing. It's much worse than raw. If we use the data cache, we get much higher, like factor 4 or 5, even higher than raw. The reason for that is what happens when you cache these things. And you have really small write requests coming from the guest. We actually end up merging write requests through the cache. So we do even better than raw. It's a nice side effect. It was not quite intended, but we'll take it. Okay, and the third problem I want to talk about is when you have internal cow, that is, you do copy and write, where the original cluster is in the same image file as we're writing to. That are the cases that I mentioned before, internal snapshots and compressed images. Then what you have to do is you have to allocate a new cluster where to write the data to. And allocating a cluster usually means, well, actually always means, you have to increase the ref count first, and then you can hook the cluster up like in a mapping. Because if QEMU crashes, or you have a power failure or anything like that, if the cluster is used, it must be referenced in the ref counts table so that you don't get data corruption. So at this point, we need a flush. We do have the metadata cache, as I said before, which can batch multiple of these. So you can just do all ref count increases, then a flush, and then all mapping updates, and it's safe. But what you need for internal cow as well is you drop the reference for the old cluster, and there the dependency is exactly the other way around. You need first to remove the mapping, and then you can decrease the ref count. So that the only thing that can ever happen in case of a crash is that you leak a cluster, but you never use a cluster that is not referenced in the ref counts table. So we end up actually doing 2 disk flushes per allocation with internal cow, which is obviously not a quite good idea. Makes things quite slow. So there are there is something missing here. Oh well. I'll just tell you what's on a slide that should be here. Right, so what are the solutions for this? We have two different solutions that we can use. The first one is lazy refcounts, which is an option that is implemented for quite a while now. So if you use lazy refcounts, we set a dirty flag in the image file, which tells basically the refcounts are not accurate. If we crash in this state, you need to run QEMU img jack before the image can be reused again. And in that case, it's not necessary to have the right order between updating refcounts and updating the mappings. So we have saved the flushes. The other option would be that we implement a journal, like journaling file systems, which will allow to update the mapping and the ref count table at the same time. So what a journal gives you is basically transactions. So you can do things at the same time. And then we would save the flushes as well. Right. So what's the current status? I have some prototype patches for the data cache. I think I'm going to post them during the 2.5 development cycle. Not sure if they will be ready for the release, but 2.5 or 2.6 I would guess. Journaling is probably not going to come anytime soon, but we do already have lazy refcounts, and if you have images that use internal cow, that is, you have compressed images or you have internal snapshots, then you probably want to use lazy refcounts. And that's it. Questions?
So your performance is stored against the data cache and the raw.
Yep.
So is the raw performance all direct, or is that?
Yes, all of this is all direct.
So then, then once you lose, if you were waiting for flushes anyway, within the data cache, it would be the same as not running all direct. So shouldn't the performance in the case of compared to data cache?
Not really. I mean, the data cache is not a full a full cache of everything. We only put things into the data cache when you would actually need a copy and write operation. So it's not in general operation.
Yeah, it's like a write behind, and only for allocating.
I know the qcow2 format has a bit for marking a cluster as always with 0.
Yes.
Is it? You said that pre-allocation does not mix well with backing images. Is it worth adding an extension to the qcow2 to add another bit that says pre-allocate my space, but read from my backing file for now, so that we don't have to allocate the cluster the moment we copy and write the data is already present and space is already reserved. We don't have to allocate.
Yeah, I thought about the same myself. It's possible to add something like this, probably even worth it, but it would mean an incompatible format change,
Right.
which is, well, what it is, yeah.
My question is, how much threads are used for this performance list? Because I think that in the thread case yes, the situation will be much worse.
I ran multiple tests. I'm not quite sure what this one is, but I did run with one thread with 16 at least.
So the other tests I ran, they were with AIO native, and I think they had a AIO depth until up to 128 threads or AIO requests at the same time. So yeah, we were thinking about locking, maybe making qcow2 slower because raw doesn't have any locking, but qcow2 does. But we didn't see any effect of that.
The problem is that as far as I can have this implementation, when you write the cluster to the whole file, you do this one by one, and we will not proceed this next cluster until the previous one is finished.
Sorry, didn't quite get that. Okay.
When you expand whole image, this new cluster at the end, you perform this.
You mean
one by
increasing
one.
the image size?
Yes.
Okay.
Not image size, but you write new.
We allocate new clusters.
Yes.
Okay.
You allocate new cluster. You wait until the write to the previous one is finished. If you write sequentially to an empty image, you have to write by 64 kilobytes chunks, and they are performed by one. You wait until previous one complete to start new. Or maybe just one.
No, usually not. We do have some locking where requests, but allocating requests have to wait if they touch the same cluster until they are hooked up in the mapping. But once the first write to the cluster is completed, in the case with data cache, even if the data is still sitting in the cache, it's not written out yet, then multiple requests can run in parallel. And as long as they touch a different cluster, they can run in parallel anyway.
Can you go to the last slide, please?
Status?
Yeah, laser outcome. So can you build a live compressed qcow2 files, and can you set this lazy refcounts feature once the image has been compressed or recompressed, or do you have to run?
You can use QEMU IMG amend to set the option, or you can actually also set it as a runtime option in -drive.
Okay, so
-drive file equals blah blah blah, comma lazy refcounts equals on.
So it's turning that on is an instant operation. It's not
Yes.
dependent on the image size or
No,
and is it default maybe for new?
no, it's not the default
Okay, thank you.
because it requires after a crash that you do the QEMU IMG check. So that's not something we want to have by default.
Thanks.
Hi, I have a suggestion for Max. Can you go to the slide where you showed the formula to calculate the cache size?
Yep.
Yeah, so basically, when I was looking at it, I realized that it's tunable, and it's probably a pain for
Yeah, well,
to do this.
there is a reason. So one reason is that once you create a qcow2 file, it's basically empty, and it has 0 length. So if you try to derive like that, like the cache size from that, the cache will be empty, and we had some problems with that, which should be fixed by now. But the other reason is that if you create like a huge image and you don't have any C.1, you don't have any application which actually does random accesses over all your disk, then you don't need the full cache size. Alberto has some patches on the list which automatically sweep the cache after a certain amount of time. So it looks through the cache and looks at all the cache entries, and if some have not been used for a certain amount of time, tunable by the user, then they will basically be evicted. And once we have that, we can probably make it the default. But as long as we don't have that, we probably don't want to have a huge RAM usage for large images, which you don't expect. But once we have automatic cache sweeping, we can think about that again, yeah.
My suggestion to you is that the LU cache size, maybe we could add a constant parameter. You could say L2 cache size from X, and then this calculation is performed automatically. So then users don't need to calculate it. Of course, then they have to spare those 4 megabytes. But the important thing is if you do that,
You're fine.
then as a qcow2 developer, you can get your name into the command line.
Oh yeah, that's great. Yeah.
Okay. I guess that's it then.